A payment system has one non-negotiable mandate. It transfers monetary value. By design, it must guarantee zero lost funds and zero double charges. It is a common engineering trap to treat e-commerce payment backends like high-volume social media data feeds, optimizing the architecture for massive throughput. That is an error in scoping. This calculation shows why. If a platform processes 1 million daily transactions, dividing that volume down to the second yields approximately 11.5 transactions per second. This is a remarkably low throughput environment. At that volume, the system handles two primary workflows: the pay-in flow, which routes customer funds to the platform, and the payout flow, which settles those funds to the merchant. We are going to construct a scalable payment backend optimized entirely for distributed state management and failure recovery. Because throughput is a trivial bottleneck at 11.5 transactions per second, the true engineering challenge is maintaining deterministic, exactly once financial transactions across non-deterministic external networks. Let's trace a naive, synchronous API request designed to move money from point A to point B. The client sends a payload and waits in a blocking state for a success response. Real-world networks degrade. A user initiates a transaction, but a network stall prevents the confirmation from returning to the client. A timeout occurs. When faced with a timeout, the immediate human response is to click the pay button a second time. The server receives the second request. Because it has no memory of the first stalled attempt, it blindly processes both. The user is charged twice. A naive system assumes the network behaves predictably. A financial system must be architected under the paranoid assumption that the network will constantly lie, delay, and duplicate data. This diagram outlines the baseline microservice architecture. A client request hits an API gateway, routes to our payment service, passes to a payment executor, and hands off to an external PSP. A single checkout event can spawn multiple payment orders if purchasing from different sellers. Handling raw credit card data introduces strict PCI compliance burdens, so our system avoids touching it. Instead, our payment service generates a unique UUID nonce and sends it to the PSP. The PSP returns a token, binding the secure session to that specific payment order. Using that token, the client redirects the user to a hosted payment page. The external PSP safely captures the sensitive card data directly on their own infrastructure. Once the card is processed, the PSP uses an asynchronous webhook to notify our internal system of the final transaction status. Decoupling the payment capture via hosted pages and asynchronous webhooks drastically reduces legal compliance risk while retaining absolute tracking of the payment lifecycle. To solve the double charge problem, we have to satisfy a specific distributed systems equation. Exactly once processing equals at least once delivery plus at most once processing. At least once delivery ensures a message survives transitory network drops. If a request fails, the client uses an automated exponential backoff strategy to retry the connection. The inherent danger here is that aggressive retries inevitably create duplicate processing requests on the server side. We enforce at most once processing by assigning an idempotency key to the request header, usually the unique checkout ID generated by the client. In the database, we apply a unique key constraint to the idempotency key column. The initial row inserts successfully. But when a duplicate request arrives with the exact same checkout ID, the database rejects the insertion. The system catches this rejection and safely returns the cached success status of the original request. The duplicate is neutralized. Database-enforced idempotency is the mechanism that makes aggressive network retries safe. When the PSP successfully charges the card, it fires a final webhook confirming the event, which writes into our internal payment service database. The payment order status updates to success. Now, we must update downstream services, specifically crediting the merchant's wallet and recording the transfer in the internal ledger. Executing synchronous API calls to these downstream services introduces the hazard of cascading timeouts. If the ledger service runs slow, the entire payment process blocks. We insert a message queue, like Kafka, to act as a decoupling layer. The payment service publishes a single success event into the queue, which the wallet and ledger service nodes consume independently at their own pace. The ledger operates on the double entry principle. This is the mandatory standard for financial traceability. The unbreakable arithmetic rule of a double entry ledger is that the sum of all transaction entries must equal exactly zero. For a $1 transaction, we record a $1 debit to the buyer and a $1 credit to the seller. The bottom line calculates to 0. Decoupling state updates through a message queue protects this double-entry ledger from microservice network failures, guaranteeing an immutable append-only audit trail. We must account for catastrophic failure. Consider a scenario where the external PSP goes entirely dark and the webhook confirming the payment never arrives. Inside our database, that payment order becomes indefinitely suspended in an executing state. The exponential backoff retries continue attempting to pull the PSP for a status, eventually reaching their maximum threshold and failing out. We divert these permanently failed messages to a dead letter queue. The dead letter queue prevents unresolvable messages from indefinitely blocking the main processing pipeline. It safely quarantines the data so an engineering team can manually triage the failure. The core limitation of this architecture is that we cannot implicitly trust that external asynchronous PSP systems will perfectly align with our internal database. To enforce absolute alignment, we rely on a nightly reconciliation job as the ultimate source of financial truth. At the end of the day, the external PSP or bank generates a comprehensive settlement file containing the final balance and all processed transactions. This diagram illustrates an automated strict diffing process. The system scans the external settlement file row by row against our internal double-entry ledger. If a webhook was dropped or events arrived out of order, the detected mismatch is routed to a finance team queue, forcing eventual consistency. A robust payment system is never defined by its raw throughput speed. It is defined by rigid idempotency constraints, its immutable ledgers, and paranoid reconciliation loops.